Today we are going to be hearing from Mike, who's going to be telling us a little bit about earthquakes and faults, is all I've heard. So I'm intrigued to...
Some shaky science. Huh?
Shaky science, good start.
Has to get the puns out early. Yeah, so I guess the motivation for this talk is recently I've been watching Aftershock, and it's reminded me of what I was doing before I came to Australia, back during my honours and masters. So I thought it'd be fun to relive some of those memories and talk about something a bit different than we normally talk about here. So the talk's mainly going to be on subduction zones because that's probably where we study earthquakes the most, but just as an introduction to I guess some of the things we'll be talking about. In 2016, I was fortunate enough to go to the Danakil Depression, which is right sort of in the belly of the East African Rift. So this is their far triple junction. And it's an incredibly tectonically active place. You have in the middle of the depression, it's 120 meters below sea level at the moment. In the middle of the depression, you have these both proper like volcanoes and also these sort of salt volcanoes and sulfur fumaroles. And this picture at the bottom here is sort of on the salt flats at 120 meters below sea level. And because, you know, the bottom of the basin is kind of dropping down as we speak, you have these huge alluvial fans that run into the basin and essentially are bordered by these big faults that, you know, the subsidence is occurring along. And when you look at those faults, it's quite interesting. You see, you know, they're very well defined. So the picture on the left here, you've got the alluvial fan, basically. You can see the nice sedimentary layering. You've got this zone that's probably about maybe 10 to 15 meters wide of really crushed up, brecciated rock. And then you've got these, you know, Neoproterozoic volcanics on the right. So there's massive amount of displacement that's occurred over the zone that's probably 15 meters wide. But then when you zoom in even closer, so that picture on the right there is taken essentially over there, right at the margin of that fault zone. You see all that action is happening over the zone. That's probably about 2 finger widths, maybe 2 centimeters wide, right? So I think that, you know, I find faults fascinating because it's where all the action in plate tectonic happens. And what you find is that action is concentrated onto, you know, very, very zones of finite thickness. And it's quite interesting to sort of look at, you know, what are the processes happening in those zones. And yeah, that's kind of what we'll be talking about mostly today. So to make that point sort of on a larger scale, I'll just sort of play you this video. It's a compilation of basically every earthquake that's happened on Earth in the last 15 years. And I'll just let it run for a bit and talk as things develop. So immediately what you see is basically the earthquakes going on all the time of varying size, and that most of them occur in subduction zones, right? You do get a few at the mid-ocean ridges and obviously in sort of tectonically active parts of the continent like the East African Rift and collisional zones, but by far most of them happen around the sort of circum-Pacific subduction zones, and particularly the really big ones, right? So in about a year's time, we'll get to December 2004, which is an important time period. You'll see we have a really massive earthquake here in Sumatra. There we go. And we all know what that represents. So what you see, there's lots of small earthquakes going on all the time, but these really big ones like the Sumatran earthquake in 2004 come along very rarely. And you might also be able to pick out that there's earthquakes happening at a range of depth. So we have, you know, particularly lots of very small earthquakes that are quite deep down to 800 kilometers. But if you pay attention, all the really big ones are all at very shallow depths, so kind of less than 50 kilometers. And we'll talk a bit more about why that's the case. So, you know, the next big thing we can expect is probably in 2011. I don't know if we want to wait to let it get there because I've got quite a few slides, so I'm a bit worried about time. Just press on.
Soundtrack as well.
Yeah, Theo on the drums. But that's basically the story, right? Like most of the sort of earthquakes are a fundamental part of plate tectonics, right? And they're how essentially plates accommodate the sort of relative motion between one another. And the point to get across is that that relative motion isn't continuous. It happens episodically and in space and in time, right? So you have sort of particularly large earthquakes tend to happen in clusters. So obviously in 2004, 2005, and 2007, we had sort of that cluster of earthquakes in Sumatra. In sort of Chile and Peru, there have also been sort of another cluster of these large magnitude 8+ earthquakes. When you look at them in time, you see as well that there's long periods where we don't have very many big earthquakes, but then there's sort of narrow patches in time where we have quite a few big earthquakes, and that's particularly exemplified by this period here between 1950 and 1970, right? We had 3 quite large earthquakes. This Chile 1960 being sort of the largest earthquake that's ever been recorded. It's a magnitude 9.5, which is, put in perspective, the Tohoku earthquake in 2011 was 9.2, so it's about 3 times larger than that, and Tohoku was pretty destructive, right? So, yeah, so that's the point to get across, and then you obviously get these periods, right? So since 1965 to 2004, when the Sumatra earthquake happened, there was this huge lull in sort of great earthquakes, so great being greater than magnitude 8 or 9. And what that shows is that, you know, there's continuous seismic activity going on all the time, but that most of the energy released happens in these massive earthquakes because they're just so massive, right? So that understanding how these big earthquakes happen is incredibly important, because obviously we want to mitigate the disasters that usually ensue when they happen. So to start off briefly, what is an earthquake? Essentially, what we know comes from that chap up there, is James Byerly, who did these experiments sort of on rock deformation back in the 1960s, and postulated that earthquakes occur by stick-slip behavior. So essentially, it's a frictional process where you're putting stress on a fault. That fault has some frictional strength. Over time, the stress will build up. That rock surrounding that fault will deform elastically, and eventually the combination of the force you're applying plus the elastic strain will cause that fault to break. And that sort of gets into this concept of the seismic cycle, right? So that process repeated over time tells you that earthquakes are going to be a cyclical feature. And you see this kind of sawtooth pattern that they showed from their laboratory experiments, which kind of speak to that. These animations not going to play. Oh, there we go. So this animation kind of illustrates that process. It's a little sort of conceptual model. You have a block that's got some friction associated with, and you're pulling on a string that's applying a force. And when the force exceeds the friction on the surface, which would represent the fault, you get a slip event, and that's essentially when the earthquake happens. And you see it is dependent on the friction. So this blue block has coarse sandpaper, it's got more grip, it requires more force to slip. And when that slip occurs, energy gets radiated, right? And so what seismologists do mainly is look at that energy, and particularly the ground motions that you can measure, to figure out how the earthquake occurred and where it occurred. So here's a nice little animation, if I can get it to play, of, so this is following the Nepal 2015 earthquake that the Aftershock film's about. And essentially, you've got all these seismometers that are set up in the United States, and you can watch the waves of this earthquake roll in. So we've already seen the P waves, now we're getting into the S waves, which are these sort of shear waves, and then the rally waves come along later. And you'll see it's quite interesting. So obviously the first waves to arrive are the waves that traveled over the North Pole to get to North America. But somewhere now you see the waves reverse, right? And they go the other direction. And those are the waves that went all the way around the other side of the Earth, and they're not coming up from the bottom. And if you let it run long enough, you'll probably see them go around once or twice, but I don't think this animation does that. So from that information, right, we can use the P wave arrival times to tell us where the earthquake occurred. So essentially you need 3 stations positioned sort of around roughly where the epicenter was. And, you know, based on the difference in time of arrival at those waves at the station, you can draw these circles and where the circles meet, that's where the epicenter was. And we can also figure out something about the plane that earthquake occurred on by looking at the polarity of those P waves. So whether the first motions go up or down tells you whether, where it was going, where it was in compression, where it was in extension. And you can say, okay, well, the earthquake occurred either on a plane going like that or like that. And usually you need some other geological information to tell you which plane that was. A brief sort of overview on earthquake size. Obviously, you saw in the animation earlier, you get lots of very small earthquakes, sort of in the sort of magnitude 2, 3, 4 range. And that, there's an exponential decrease in number of earthquakes, but that an exponential increase in the sort of power and destructiveness of those earthquakes. This is a log scale, so magnitude 2 or 3 is 10 times greater than 2, and 4 is 100 times greater than 2, and so on. So, but when you're getting up to magnitude 8s and 9s, you're getting into something like seriously destructive events. So, Krakatoa eruption, they're estimating here is probably an 8.5, and the Hiroshima bomb is probably only magnitude 6. Right? So, well, have I gone all the way to the end? And essentially what that size relates to is the area that you slip, right? So magnitudes 2 to 4 is you're slipping areas of kilometers, and every sort of step up by 2 in magnitude is essentially an order of magnitude and length scale that you're slipping. So 5 to 6, you're probably 20 kilometers by 5 kilometers. And then the really big events, you're slipping thousands of kilometers along a fault, which is truly massive. And the energy required to do that is quite phenomenal when you think about it. So where earthquakes occur, mostly in subduction zones, once you've figured out where they are and you can locate their depth, you can plot them on diagrams like this. And often you see that they map out the subducting slab, and most of them occurring at shallow depths, right? When you zoom in closer, and so this diagram on the left here plots not just the frequency distribution of where those earthquakes occur, but also scales it to the energy released during those earthquakes, so the seismic moment. See, most of the energy released is in this very narrow band, right? Probably between 15 and 25 kilometers depth. And that relates to this idea of a seismogenic zone. There's a particular depth in the crust where earthquakes can nucleate, and particularly the big ones can nucleate. And above that depth, there's a more stable region where you can't nucleate big earthquakes, but earthquakes can propagate through. And below some depth as well, probably 25, 30 kilometers, you get into another stable region where earthquakes can't nucleate. And we think that relates to sort of changes in physical properties of rocks. So at shallow levels, you have rocks that are very probably unconsolidated. They don't have a lot of strength, so they can't sustain sort of large forces. In the middle crust, your rocks are gaining frictional strength that can sustain large forces. And then at some depth, there's a change in deformation mechanism from frictional to viscous deformation. And that results in a sort of decrease in strength with depth. And again, your rocks can't sustain large forces. So in terms of subduction zone, that's what we think this looks like. You have your lower plate coming in, the accretionary prism that gets formed as you sort of accrete material onto the upper plate. And you have this sort of initially dominantly aseismic area that might have sort of patches that can nucleate earthquakes. And then you get into your seismogenic zone. And again, what I'll explain a bit later is how this patchiness occurs, right? So the seismogenic zone isn't uniformly seismogenic. You have patches that are more seismogenic than others. And we'll discuss later why that's the case. And then you get this transition zone out of the seismogenic zone at about probably 350 to 400 degrees. But that you see there is some sort of patchiness there as well. And I'll explain later about some of the phenomena we find down there that are quite interesting. So just to give you another sort of animation about what's going on. Essentially, you have this incoming plate that's coming down. Part of that fault surface, right? The subduction megathrust is locked. Because of that, the upper plate deforms and accumulates sort of elastic strain energy. And what you see if you have a GPS on the surface here, that GPS gets dragged back with the lower plate that's going down. at some time something bad happens. Yeah, and yeah, depending on the dynamics of the earthquake, you can often get quite a devastating tsunami. So Tohoku is a very nice earthquake to sort of illustrate this process, because the Japanese have an insane amount of GPS stations on their island. So each of these blue dots is a GPS station, and they're plotting little vectors, and you'll see just after the earthquake happens, there's this huge shoot forward. All those GPS stations just jump forward a couple of, I think, meters even. And then a bit later on, there's an aftershock down here. You see that's much smaller. There you go. It's quite cool. You can see those waves also ripple out through the GPS stations. And this video is quite long. I don't know if I'll play the whole thing, but we all know what happened afterwards, right? When those faults break and you displace a large volume of seawater, you get a tsunami. I just thought this is an interesting video to show, because it's apparently this town had the highest seawall in the world, right? So it's meant to be the most protected. I think it's like a 3-meter high seawall, 18 feet. And I'll just run to the point where the tsunami really comes in, because you see it just completely swamps it. Like, and it gives you sort of quite a visceral feel for the power and energy of these things. It's just pushing cars around like they're toys. And yeah, so now that wall's completely underwater almost. Got this log jam of cars that are piling up there. And if they'll pan to the left now, I think. But so I don't know if you remember, there were a few buildings and stuff there before. They've just been completely wiped out. I'll stop it there, because that's the main point that I wanted to get across by showing that, is that these things are incredibly destructive when they happen. So it's quite important that we know how they happen and what are the processes that's causing these earthquakes, because if there's any way you can kind of predict them or get a feeling for when they might happen, it can save lots of money and lives. So the reason the Tohoku earthquake was so devastating and caused that massive tsunami you've just seen is because a lot of slip happened very, very close to the trench, right close to the surface where that plate's intersecting essentially the seafloor. So what they've done in these images is use the GPS data and also the information they gather from seismic waves to reconstruct where that most of the slip happened on that plate interface. And you see it initially started quite deep down at about 30 kilometers, but then very rapidly pushed forward and a huge amount of slip. So in this model, it's about 35 meters. In other models, it's closer to 60 meters, I think, or 50 or 60 meters occurred right at the trench, right? And because the slip's occurring so close to the sea floor, it flicks up the plate, displaces a huge volume of water. which they estimate here to be maybe 10 meters during the event. And because you displace all that water, you cause a huge tsunami. Similar thing happened in the 2004 Sumatran earthquake. What's quite interesting about this one is that when you reconstruct the slip distribution, it didn't occur in one patch, but in multiple patches over a massive distance. So this is going from 15 latitude, 15 degrees north to 2 degrees. So that's almost 1,000 kilometers long of subduction zone that slipped in these 3 patches, and again, up to 20 meters over, maybe a period of 2 minutes. In this event, you didn't get as much slip right at the trench, but what they think happened was, I don't know if you remember on the diagram I showed previously, you have the accretionary prism above that has those faults coming off it. They think one of those faults in the accretionary prism slipped as well. And because they're at a much higher angle, they can displace more seawater. So by studying sort of co-seismic slip distributions, we can get a sense for the sort of patchiness of these subduction faults, but you can also get a feel for it by looking at GPS data from the periods where, when you don't have these big earthquakes. And you can see that in this study here. So it's from the Aleutian Island arc, which is on the northern Pacific. And this subduction zone has also historically had a few big earthquakes. So the 1964 9.2 in Alaska is the second biggest earthquake that's ever been recorded. And various other patches on this subduction margin, you've had a few other big earthquakes at various times. But there's this interesting gap here as well. It's never failed in a big earthquake. And what you see when you look at the GPS data sort of from these islands is that there's a huge along strike variation in velocity. So getting up into this part of the region near Kodiak Island, which is within the sort of co-seismic slip area for the 1964 earthquake, you see that the GPS stations are moving backwards, with the Pacific plate as it's coming in. And if you remember from the little animation I showed earlier, that tells you that that part of the subduction zone is locked, right? So it's dragging the upper plate back with it. When you move along strike, you see that that velocity decreases, right? And that down here, sort of in the region above this seismic gap, almost, the upper plate isn't moving at all, really. So that's telling you that the subduction zone is just creeping. It's not locked. And the upper plate's pretty stable. So again, it's telling you there's some heterogeneity in how the subduction zone locks the long strike. And it's not just one patch that gets fully locked or fully opened. That there's some heterogeneity, and that's essentially what they're mapping here. And what they identify in the study is that where that transition occurs, right, from the locks to the sort of creeping portion, you have this huge change in the structure of the oceanic plate. So you start to get a sense that maybe it's what's controlling where these earthquakes are occurring or where the locked portions of these faults are versus isn't, is somehow controlled by what you're putting down there. So that's kind of an overview of big earthquakes. What we've found in the last 2 decades is that faults don't just fail in big earthquakes, right? There are a bunch of other mechanisms by which that relative motion can be accommodated. And one of those are these, what's being called slow slip events. So these are events that don't radiate seismic energy at all. You can't identify them using seismology, and you can only identify them using geodesy, so using these GPS stations. And what you see is, like we showed previously, at times the plate boundary fault is locked. These GPS stations and the upper plate are getting dragged down with the subduction zone, but then periodically they pop back, right? Over quite a short period of time, usually days, weeks, sometimes months for these longer events. And you can reconstruct where these events occur. And in this case, this is one on the Hikurangi margin in New Zealand. It occurred very close to the trench as well. And we're not having huge seismic sort of slip. So slip magnitudes are much less. In this case, it's a few centimeters, 25 centimeters. But still, it tells you that you're releasing that energy somehow. They've mapped where, in the Hikurangi, they've mapped these sort of slow slip events in a number of places. So the one I just showed you was one of these very shallow ones here, but you find them at much deeper levels as well, right? So in this case, they're sort of above 12 kilometers and below 25 to 30 kilometers. And that's quite interesting as well, because if you remember earlier, that's roughly where those transition zones are, right? the upper part of the seismogenic zone and the lower part of the seismogenic zone. So we find other interesting phenomena in those regions as well. So there's this seismic phenomena now that we can measure on seismometers called non-volcanic tremor. And it's initially, they thought it was just seismic noise, right? This, like you see at the bottom here, it's just slight variations in the seismometers just from ambient noise. But it's kind of now been recognized as a distinct class of earthquake. So it's not like your typical normal earthquake where you've got distinct PES and rally wave arrivals. There's kind of no distinct body wave arrival, and you just kind of get this increase in noisiness and decrease in noisiness. And how it's distinguished is when you look at the frequency spectrum, you see that, at the very low frequency end, it's quite similar to seismic noise, but in your sort of 1 to 10 hertz range, it's significantly elevated, right? Like you would see for a normal earthquake. But then at the high frequencies, so above 10, it's back to noise, right? And that's kind of the characteristic feature of these events and what makes them distinct from normal earthquakes. And just comparing, I think you can see these numbers here, 10 to the 3 versus normal earthquake, 10 to the 6. They're very, very low magnitude. They're almost barely distinguishable above seismic noise. So it's telling you that they're probably very, very small sort of length scale slip events or some kind of fracturing process that's happening on very, very small length scales. And what's curious is that when you map where these tremor events occur, they almost are exactly co-located where you find these slow slip events, right? So where the plate boundary is creeping without radiating seismic energy, you're getting like this crackling and popping. I kind of imagine it like Rice Krispies, or the noise they make, like it's that kind of thing. And they often occur sort of in the down dip region of your seismogenic zone, just sort of below where you normally get big earthquakes. And here is, so this is in Nankai, Japan, where, they've co-located these things extremely well. And this is from Cascadia, where you see there's this sort of periodic slow slip that's occurred almost very regularly. And that whenever you have those slow slip events, you get an increase in tremor activity. Got another animation just to show how this occurs. Well, so you can see that slipping that's happening in the sort of down dip region creates a sawtooth pattern. Uplifting music. Okay, and this slide just shows that, we see these sort of features on almost every subduction zone where we've looked for them. So the best ones are probably in Nankai, and that's, I guess, because the Japanese have an insane amount of GPS stations and seismometers. But you find them in Cascadia, which is on the just near Vancouver. My aunt and uncle's house is right beneath that patch there, actually. And then in Alaska as well, and in New Zealand, like I've shown previously. So it seems to be a fundamental part of how sort of plate tectonics and subduction zones work, but we don't really know, what are the processes that's causing this behavior. And this slide was a paper by Peng and Gomberg in 2011. They kind of tried to sort of, pitch this holistic perspective, right? That you have almost two classes of earthquakes in the broad sense, right? You've got your normal regular earthquakes that happen over very short duration, so seconds to minutes, but it released a lot of energy in that short time period, right? but you get this other class of slow earthquakes or slow slip events that release comparable amounts of energy, right? Because these slow slip events slip huge portions or large lengths of the subduction zone. They release large amounts of that elastic energy, but they happen over such long timescales that they don't radiate huge amounts of seismic energy. And again, it makes the point that faults don't just slip by stick slip behavior. There's a range of other processes that's happening in these fault zones that we kind of need to get a handle on to understand how they work. So I've talked a lot about seismology and geodesy, and you're probably wondering, like, why do geologists need to care? And the main point is that, well, these things are happening in rocks, and the seismologists can identify these things, but they can't tell us what's happening down there because we can't access them. So us as geologists have to go and sort of find analogs of those environments and see if we can identify the processes that might match these geophysical signals that we're seeing. And as I pointed out at the beginning of this talk, a lot of, to make the maths work, and sort of seismologists have to imagine these faults as sort of mathematically flat planes. But I think what has come out of earthquake geology is that it's the fact that these shear zones aren't flat planes, that they're tabular shear zones, and they often have a range of different rock types with different properties in them that results in this behavior. And that's kind of what we'll see now. So some of the questions we're probably going to try address is, what's controlling these transitions at the up dip and down dip part of the seismogenic zone? It's clearly changes in the rocks that are going down there. What are those changes exactly? And what we can identify these slow slip and non-volcanic tremor events, but what physical processes do those events represent, right? And what controls where they occur? So I'll start with the up dip seismic transition. The up dip part, or the shallow parts of these subduction zones, are accessible to us. We can go, and there's been a number of ocean drilling programs for drilling into the incoming sediment pile in the subduction zones and into the shallow parts of the accretionary prism and looking at what are the changes happening in these rocks. And, well, they're not really rocks at that point. They're still fluid saturated sediments. And what you see is that as these rocks get buried, there's a portion of that sediment that is accreted onto the upper plate, but some of it gets underthrust beneath the accretionary prism. And as that underthrust sediment gets buried, it undergoes a range of sort of diagenetic and low-grade metamorphic processes that essentially cause it to expel a lot of its fluid. So they also get compacted, and that pore space destruction pushes out a lot of fluid. But then you have your clay minerals like smectite that transform to illite, and that process as well causes a lot of fluid to be released. And then processes like cementation destroy even more pore space. And yeah, that's illustrated quite nicely in this diagram here. So they're looking at the sort of hydraulic conductivity of these sediments as they get sort of buried at some distance from the trench. You see they start out quite high and then exponentially sort of decrease quite rapidly. And what that means is that at the shallow level and along that subduction interface, you've got the zone of quite high pore pressure, right? Because that fluid is being pushed out, it has to go somewhere. And if there's permeability, it can just flow up, and you do find lots of sort of hydrocarbon and fluid seeps in these accretionary prisms. But as the rocks get more consolidated, that fluid can't just escape through porous flow. It has to actually hydrofracture the rock. And maybe that hydrofracturing process is what's causing some of these sort of tremor events that we see at shallow levels. When you look at exhumed parts of accretionary prisms that might contain rocks that sort of formed in this kind of environment at shallow levels, you see evidence of that process, right? So this is the Crystals Beach complex, which is part of the Otago schist in South Island, New Zealand. It contains rocks of quite low, sub-green schist facies metamorphic grade. And what you see is these zones of sort of very chaotic rock assemblages. So you've got these sort of shales, or I don't know if you call them shales, essentially still mudstones that have these blocks of sandstone intercalated with them, and they're cross-cut by all these fractures. So we think that what these rocks are called is melange rocks. You might have heard the term, and what they represent is probably part of that subduction thrust interface that's been pushed into the accretionary prism. And when you look at the geometry of these shear fractures and the sort of veins that form between them, you see it's quite interesting, right? They have these extension veins that form at almost 90 degrees to the shear angles, or to the angles to the shear planes. And mechanically speaking, that, well, one, we know veins form sort of, they open up perpendicular to the least compressive stress, so they contain almost, or parallel to the greatest compressive stress. So it tells you that these faults were active sort of at very high angles to the greatest compressive stress, which is mechanically quite unlikely, right? So you can think of like if you put your hand on the table and you push hard down, it's very hard to move your hand, right? Pushing down being sigma 1, but if you let go of sigma 1, then it's much easier to slide your hand, right? So how are these faults moving if they're being sort of, the normal stress on them is so high? And the only way to explain that is by having a very high pore fluid pressure, essentially. You're pumping fluid through these fractures, and that's lifting up the sigma 1 and allowing these faults to slip. So it's consistent with what the hydrologists are telling us. What you also see is that these melange rocks can be quite heterogeneous themselves. So sometimes they can contain lots of sandstone, right, with very small amounts of mudstone in between. And other times they can have lots of mudstone with very small sandstone lenses. And Aki's idea was that, perhaps this mechanical heterogeneity, right, in terms of having rocks of varying competence, or varying proportion of rocks of different competence, I should say, might explain why you get this patchiness in subduction zones. So in these unstable regions, potentially you have lots of more competent rock that is quite mechanically strong and can sustain stresses, right? And then slip eventually in these bigger earthquakes. And then perhaps these sort of more stable regions where you don't see earthquakes nucleating might reflect places where you have lots of weak rock, and that weak rock can deform by sort of aseismic deformation mechanisms like dissolution, precipitation, creep, and those kind of processes. So fluids seem to be quite important at shallow levels, right, in terms of explaining tremor and some of the faulting processes we see. So it kind of begs the question is, can you translate that sort of to deeper levels as well? And what Ake and Johan tried to do was look at, especially the deep tremor in some of these subduction zones. Does that occur where you get dehydration reactions? So potentially from your the oceanic crust, because we know the oceanic crust contains a lot of fluid as well, especially in minerals like lawsonite, if they're blue schists, or chlorite, if they're green schists. And so they did some thermodynamic models for the oceanic crust and showed that on the kinds of geotherms that you find in Shikoku, so the Nankai subduction margin, the pressure or the depth where that tremor occurs correlates pretty well where you expect lawsonite to break down. And when lawsonite breaks down, it releases a lot of fluid. So that's quite an interesting finding. And then in Cascadia as well, along a warmer subduction zone, right? So being a warm subduction zone, you don't form blue schists, but you probably form sort of more green schist or epidote and fibrillite facies rocks. You see that where, again, the pressure and depth where that tremor occurs correlates almost exactly where chlorite breaks down to epidote. So it's telling you that these metamorphic dehydration reactions at deeper levels are probably quite important for controlling that tremor process at the down dip region too. So, like we showed earlier, can we find rocks that have been exhumed from that sort of depth to test this hypothesis? So where I got involved with this stuff was in Namibia with Ake and Johan, was basically trying to do exactly that. So in the Damara belt, you have as a Neoproterozoic mobile belt that formed between the Congo craton and the Kalahari craton about 540 million years ago. And essentially what you have there is an old accretionary prism that's very well preserved. So it initially formed probably during opening of the Comma Sea, but eventually that sea closed and you have the sort of imbricated accretionary prism in the southern zone here, and then the old arc and back arc in the northern zone. And this is very high temperature rocks in there. So our study, where we were looking, was mainly focused along this margin here, right at the sort of interface between the craton and the accretionary prism. So what you find there are rocks that look like this. So you have these essentially amphibolite facies, palitic, semitic schists that are intercalated with these lenses of metabasalt, which are now this amphibolites, so hornblende, plage, quartz, and a bit of titanite. But what you find, particularly in the metapalitic lithologies, is these quartz veins, right? And those quartz veins have been folded and turned into these sigmoidal lenses, which tells you they've sort of, but they're kind of to varying degrees as well. So some are more lenticular than others. So it shows you that those veins were forming while these schists were creeping viscously and deforming. And what you also find is the metabasalts are typically quite boudinaged, and in those boudin necks you have these quartz veins as well. And I don't know if it's quite clear, but you can see that some of the fabric in these polytic schists wraps into those boudin necks, right? Just telling you that while these schists were creeping viscously, right, you had probably fracturing of that more competent boudin. And essentially, Aki's idea was that this process could reflect that like slow slip and tremor process, right? So the viscous creep is going to be aseismic. You can slip a fault viscously without radiating any seismic energy, and he did some models to show you can do it at the strain rates you need to match the velocities you see from GPS data, but that this fracturing of those more competent rocks within that viscously deforming matrix might represent that sort of cracking and tremor that you see seismically as well. So getting to the end now, that covers subduction zones, but what we find as well is that these seismic signatures don't just occur in subduction zones, you find them in sort of continental fault belts as well. So this is an example from Taiwan, where you've got these similar kind of tremor signals. In this case, they haven't, it's not just occurring spontaneously, they've actually been triggered by seismic waves that passed through from the Tohoku earthquake, right? So when that, we saw in the animation earlier, when that earthquake occurred, it shot out these waves, right? Those waves traveled down to Taiwan. And as the rally waves passed through Taiwan, you started to get this cracking and tremor. And that's quite an interesting feature as well, right? Because why would just, these seismic waves passing through the crust cause it to start breaking and cracking? And what does that tell us about the stress state in the crust there? It kind of implies that, I think from the amplitude of these waves, they calculated that the stress change was probably on the order of kilopascals, 5 to 10 kilopascals maybe. So it's orders of magnitude lower than the typical strength of these rocks, right? If you had to fracture them from an intact state. So it's either telling you that, what it's telling you probably is that the crust there is incredibly close to failure and you don't need a lot to really push it to break. And when you see where these tremor signals occur, is that they tend to occur in areas where the VP-VS ratio is quite high. So VP-VS is a good indicator of where you potentially have fluids, right? Because fluids can't propagate shear waves, so the shear wave velocity decreases, VP-VS goes up. So when I was back in South Africa last year, I was sort of driving around the Cape Fold Belt looking for things to do, basically, keep busy. And I think we found an area that kind of can address this question of why we see these sort of remotely triggered seismic events in Taiwan. So the Cape Fold Belt is probably somewhat analogous to Taiwan. It's a Permian fold belt that formed along the southern margin of South Africa. It's subsequently been extended, but particularly in the foreland region, you don't see as much extension, so the old compressional fabrics are quite well preserved. And there's, you can see the lovely image from the International Space Station there. It kind of runs Cape Town somewhere down in the southwest corner there, and it runs about 800 kilometers along the coast to Port Elizabeth, where Taryn's from. And when you cross-cut these mountains, you get some spectacular views and scenery of these mountain passes with the Ordovician quartzites. And then I think this image is from Meerungspoort, which is pretty, going through this Cape supergroup here, basically. And then you pop out, you get into the shales of the Karoo Basin, which is what I'll talk about now. So what you see there in these sort of undulating folds is that they're cross-cut by this big fault zone. And that fault zone has a number of smaller structures that are associated with well, but it's also cross-cut by these later fractures. And particularly along one of those fault zones, again, there you have the fault zone and these extension veins that are almost perpendicular to the fault zone, right? Which is what we've seen in subduction zones as well. And not just along some of those fault zones, also you've got these slick and fiber veins that are parallel to the bedding. And then in the more competent rocks, adjacent to the slick and fiber veins, you have extension veins that are again perpendicular to the bedding. And that's quite clear on the stereo nets there as well. And basically, it's the similar mechanics to what we were talking about earlier. If you assume that these veins, and you can sort of make geometric arguments that these veins had to have formed during slip on these fault zones, it's telling you that those fault zones are slipping at very high angles to your maximum compressive stress. And for the orientation of these fault zones, they're steeply dipping now, almost 70 to 80 degrees. That can only occur if your frictional coefficients are very low, or again, at normal frictional coefficients, if your differential stress is low and your effective normal stress, so basically fluid pressure, is quite high. Essentially, you can push your Moore circle down to the extensional area of your failure envelope. So I think that's it. Basically, the idea for how that's occurring is that during sort of compressional deformation in the Cape fault belt, so sort of what's probably happening in Taiwan at the moment is that we have this sort of older Precambrian basement that contains a lot of shales and sort of even some metabasic rocks that are potentially quite fluid rich. And as you bury that stuff, you release those fluids through metamorphic dehydration reactions. And the Cape Formation rocks are quite permeable. They're these heavily fractured quartzite, aronite, smiley, you probably remember. And the fluids are going to be able to escape through those, but when they hit the crew, you've got very, very fine-grained shales. There's a big sort of dimectite or glacial unit sort of near the base of it as well, and that's very impermeable. So it's probably that contact area between the Cape groups and the crew groups. You would have sort of had this seal that would have prevented those fluids escaping, and you could build up these overpressure zones and sort of get these kind of faulting processes we see evidence for. And I think that's potentially what we're seeing in Taiwan as well. You've got some fluids that are coming up through the crust there, and they're hitting some patch where those fluids can't escape, and so the fluid pressure is building up. And that means that in that area, the crust is very, very weak, essentially, and very sensitive to small changes in stress, which can cause these sort of microseismic events we see. And that's it, really.